Let z1, z2, and z3 be three distinct complex numbers, and let w sub 1, w sub 2, and w sub 3 be another three distinct complex numbers. We are going to prove that a Möbius transformation or linear fractional transformation f exists, such that f of z sub 1 equals w sub 1, f of z sub 2 equals w sub 2, and f of z sub 3 equals w sub 3. F of z can be written as the quantity az plus b divided by the quantity zz plus d, where a, b, c, and d are complex numbers, and the discriminant ad minus bc is not equal to 0. We are also going to show that there is only one such Möbius transformation that maps z sub I to w sub I for I equals 1, 2, and 3. We carry out the proof of the existence of f indirectly. For the existence proof, we use an intermediate set of points v sub 1 equals 1, v sub 2 equals 0, and v sub 3 equals the point at infinity. We first find a Möbius transformation G, such that g of z sub 1 equals 1, g of z sub 2 equals 0, and g of z sub 3 equals infinity. Let g of z be equal to the quantity a sub g times z plus b sub g divided by the quantity c sub g times z plus d sub g, with the non-zero discriminant a sub g times d sub g minus b sub g times c sub g. Let us suppose that c sub g is 0. Then a sub g times d sub g cannot be 0, so that d sub g must be non-zero. And so, plugging in z sub 3, we find that g of z sub 3 is finite. And this contradicts one of the requirements for g. Therefore, c sub g cannot be 0. We divide every term in g of z by c sub g. Let a sub 1 be equal to a sub g divided by c sub g. Let b sub 1 be equal to b sub g divided by c sub g. And let d sub 1 be equal to d sub g divided by c sub g. Then g of z equals the quantity a sub 1 times z plus b sub 1 divided by the quantity z plus d sub 1. If g of z sub 3 is infinity, then g of z should tend to infinity as z tends to z sub 3. And so z sub 3 plus d sub 1 must be 0, so that d sub 1 must be equal to minus z sub 3. And so the quantity a sub 1 times z sub 1 plus b sub 1 divided by z sub 1 minus z sub 3, which is g of z sub 1, should equal 1. And the quantity a sub 1 times z sub 2 plus b sub 1 divided by the quantity z sub 2 minus z sub 3, which is g of z sub 2, should equal 0. We solve these equations simultaneously for a sub 1 and b sub 1. We get a sub 1 equals the quantity c sub 1 minus z sub 3 divided by the quantity c sub 1 minus z sub 2, and b sub 1 equals minus z sub 2 times the quantity z sub 1 minus z sub 3 divided by the quantity z sub 1 minus z sub 2. Plugging these into the formula for g of z, we get the formulation for g of z in terms of z sub 1, z sub 2, and z sub 3. G of z can be rewritten as the quantity z minus z sub 2 divided by the quantity z minus z sub 3 times the quantity z sub 1 minus z sub 3 divided by the quantity z sub 1 minus z sub 2. This last quantity is called the cross ratio of z sub 1, z sub 2, and z sub 3, and is often written as opening square bracket z, comma z sub 1, comma z sub 2, comma z sub 3, closing square bracket. And we have a cross ratio formulation for g of z. We find a second and twin Möbius transformation to g. We call this second transformation h. H maps w sub 1 onto 1, w sub 2 onto 0, and w sub 3 onto infinity. H is exactly the same as G, except this time H maps the w sub i's onto the v sub i's instead of the z sub i's onto the v sub i's, which is what G does. And so, modifying the formulation for G of z, H of w equals the cross ratio of w, w sub 1, w sub 2, and w sub 3, and is equal to this quantity. We set H of w equal to v. In another video lecture whose title is Möbius Transformations Introduction, we had shown that the inverse of a Möbius transformation exists and is also a Möbius transformation. And so H inverse exists and is also a Möbius transformation. We can find H inverse directly by solving for W in terms of V. W in terms of V is equal to this fraction. This is H inverse of V. We now make the claim that f of z equals H inverse of G of z. In the video lecture Möbius Transformations Introduction, we also had shown that the composition of two Möbius transformations is a Möbius transformation, so that H inverse of G, and therefore f, is a Möbius transformation. We just need to verify that f does what it is supposed to do. We check H inverse of G of z sub 1. G of z sub 1 is 1, and recall that H of w sub 1 is 1, so that H inverse of 1 equals w sub 1, so that H inverse of G of z sub 1 is w sub 1. The viewer can check that H inverse of G of z sub 2 is w sub 2, and that H inverse of G of z sub 3 is w sub 3. And so indeed, f does what it is supposed to do. This concludes the existence part of the exercise. To prove that f is unique, we suppose that another Möbius transformation K exists that does what f does with z sub 1, z sub 2, and z sub 3. That is, K of z sub 1 equals w sub 1, K of z sub 2 equals w sub 2, and K of z sub 3 equals w sub 3. The existence of the second transformation K is conceivable at the moment because we could have arrived at the existence of f by using a different approach, or by simply using a set of v sub i's different from 1, 0, and infinity. Let's examine G inverse of H of K of z sub 1. K of z sub 1 is w sub 1. H of w sub 1 is 1. G inverse of 1 is z sub 1. And so G inverse of H of K of z sub 1 equals z sub 1, so that z sub 1 is a fixed point of G inverse of H of K. Using the same idea, we can verify that G inverse of H of K of z sub 2 and z sub 3 are z sub 2 and z sub 3 respectively. And so the function G inverse of H of K has at least 3 distinct fixed points. Now, G inverse of H of K is a Möbius transformation, since it is the composition of 3 Möbius transformations. And so we should be able to write G inverse of H of K of z in the form the quantity az plus b divided by the quantity zz plus d, where a, b, c, and d are complex numbers, and ad minus bc is not equal to 0. The fixed points of G inverse of H of K all satisfy the equation the quantity az plus b divided by the quantity zz plus d equals z. We cross-multiply and move all the terms to the right side, and we have 0 equals c times z squared plus the quantity d minus a times z plus b. Because of the fixed points z1, z2, and z3, this equation is supposed to have at least 3 solutions. But the equation is quadratic, and can have no more than two solutions. And so we have a contradiction. And so the equation cannot be quadratic, and so C must be 0. But this leads to another contradiction, because now the equation is linear and can have no more than one solution. So the equation cannot be linear, which means that D minus A is equal to 0, or that D equals A. We are also left with B being equal to 0. Therefore, G inverse of H of K of Z is Z. We apply G to the left side of each side of this last equation. We get H of K equals G. We apply H inverse to the left side of each side of this last equation. We get K of Z equals H inverse of G of Z. But F of Z is also equal to H inverse of G of Z. Therefore, the Möbius transformations F and K are one and the same, and F is unique.